each of those in each of those elements there. All I know is that the integral of H around the whole closed loop has some value, but I don't know what it is in each region. So I can rewrite this as the sum over all the terms, over all the bits. So I could have a whole bunch of different magnetic materials, you know, region 1, 2, 3, 4, 5, and the gap happens to be one of those. All right? Of the magnetic flux determined somewhere around the loop, but that's going to be the same no matter how wide or fat or whatever that region is. The flux is going to be the same, and that's reasonable because mu is much, much greater than 1. So any magnetic field that's outside of the core is going to be tiny compared to what's inside the core. Like 1,000. Oh, yeah.
Is that flux the B field or the H field?
That's the B field.
So that's the actual B.
So I have to put a few more things in there in order to make that work out, all right? Because the H field is, and I hate to write it this way, but I am, is B over mu. Right? So I've got my magnetic flux here, right? But this is magnetic field times area. Actually, maybe I'll write that here. So I've got H is equal to B over mu. Now what I'm going to do is multiply top and bottom by the cross-sectional area. All right? Then I'm going to say the one thing that I know is constant throughout the circuit as I go around the circuit is the flux. So I'm going to rewrite that as phi b over mu a. Okay? So phi b over mu of the ith portion of the circuit times the area, the cross-sectional area of the ith portion of the circuit. And by the way, that actually also takes care of, if I did this, the flux through that is the same as the flux through everything else. It's not allowed to leave the circuit. So I've just increased the B field in that region tremendously. What? You're not liking this? It's engineering.
Hence
right?
the reason we don't like it.
And I lost an Li. Okay, you notice here that one of these things is not like the others. This one here, no one got that.
No, I got it.
Sesame Street. All right, this one is the same everywhere, and this depends upon the material that we're passing through. This is a portion of the circuit. So I'll rewrite that as the magnetic flux in the circuit times the sum, and you're going to love the word that we use for the next portion here, L sub I over mu sub I, A sub I. That should look sort of philosophically familiar to you here. And that I've got something which is an intensive property of the material, and something else which depends upon the geometry.
The magnetopacitance.
I like that. But we have a better word, I think.
Oh
I'm fooling with you here. That's what it's called. It's called the reluctance. Not the resistance, but the reluctance. It goes along eventually. Whereas the resistance says no. The reluctance just sort of says let's make it look like a script R. Reluctance. All right? That generally can be used to solve a lot of problems. Now that I really just introduced the language here, I'm going to come back and sort of use the torn apart version and discuss how we figure out what the magnetic field is in that problem there. Okay. I say maybe the most important aspect of this portion of the class, this class, is that electrical engineers are going to talk using this language as though, oh, it's obvious, this is what you do, and you have to set it up, here's the reluctance of the circuit. And you don't want to be in the room thinking I'm an idiot when they're talking about this. So having seen a little bit of it, and a little bit of knowledge covers up a lot of ignorance, or no.
A little knowledge is a dangerous
it's
thing.
very dangerous, yes. But when you're talking about like being in a room with other people and being at least able to pretend that you know what's going on, it's good to have some idea of what they're talking about.
Amazing.
All right. So this actually, this approach, if mu is a constant for each of the materials independent of the field, just allows you rather rapidly to figure out what the magnetic field is based upon the material, that is knowledge of mu, knowing the cross section and at each region, and knowing what the, I've already forgot,
L?
Motive forces. Right? If you know that, then you can calculate what the magnetic field is going to be in any region. Right? And it's particularly useful when you've got a structure like this. Let's finish this, and you want to know what it is there, and then you just use that idea that the flux, the magnetic flux, is a constant. Right? So, but I'm going to do an example. Yeah. I'm going to start with the idea that mu is about 1,000. We don't know exactly what it is, but it's going to be some function like that. Maybe we're out there on that curve. I think I'm going to work with numbers here as well. But my numbers are now going to be MKS, because that's where I took the example from. I'm going to say that the current is, yeah, let's do it this way. 1 amp. The number of turns is 100. And just to make life easy for myself, I'll make that distance 1 meter. And then I will, I need to know the cross section. And let's say the cross section is 4 square centimeters, just to mix units up. That pretty much covers it. All right. So, come back over there. The magnetomotive force
That
is
thing.
N times I, which is 100. And H is going to be then, H is going to be approximately 100 over 1 meter. So H is going to be 100 amps per meter. With no mu0 thrown in, right? Just to give us an idea of what's what's going on.
Wait, mu 0 or
I'm undoubtedly going to screw up the multiplicative constants. I'll try not to, but I'm going to do it. And then I will attempt to correct it in the notes that I post. I haven't posted these yet. All right. So going back up there, I can write H in the core. It's called this material here. Okay. Times the length of the core. Oh, I forgot to say how wide the gap is. Let's make the gap 1 millimeter. Right. So H core times length of the core plus H gap times length of the gap is equal to Ni. Problem is that I don't know what H is in either of these regions. And so what I want to do is to try to rewrite at least some of this in terms of the flux. And then using a curve like this, I can figure out what H is and find out what flux corresponds to that. And then given that, I can make a correction to the equation and come back, recalculate H, and sort of home in on the actual H and actual B. Right? So it's an iterative process, but if mu is perfectly linear, you don't have to iterate, you're there. Okay? So, what I'm going to do though is recognize that from our approximation that the magnetic flux is constant all the way around. But I still want to find out what H in the core is, because that's going to determine what B in the core is. So what I'm going to do is convert this part of the equation into flux and leave H here. And then I'll come up with a relationship between H in the core and the magnetic field and the flux. And then I'll have, so I have the material property there. And by the time I'm done, I'm going to come up with, it'll be linear, so I'm just going to draw it. I come up with, this comes from my circuit equation, what I'm about to do. Okay, I have a relationship between H and B that must be obeyed by the circuit. And a relationship between H and B in the core that's dependent upon the material. And then where those two cross each other is the B and the H in the circuit, in the core, actually. Okay. That was to explain why I'm going to do something that seems totally tautological here. H core, L core plus. By the L gap. But now I have to make a correction here and put in, I want to go from H to B, I put in mu naught A gap. So I just switched to MKS on U. But I wanted to be explicit. I don't want to have a 1 in there. I want to be explicit about that that's the mu of the gap. And because I wrote this as Ni here, it turns out that I need a mu naught there in order to convert H to B. So there's where I might have gone wrong in my conversion of all units, but I'm going to leave that there because I can't do that. I broke the magnetic field out so that I can see it explicitly in here. And I remind you that one of the horrible simplifications that I made here is that the magnetic field is the same here as it is there. It is that. but we're going to use that approximation. And that's reasonable if the cross-section is small compared to this distance. Right, so this works for, taking a 1 centimeter rod of iron and bending it around, for example. It works well for that. Anywhere else, it's not such a great approximation. Yes?
If those A's are cross-sectional areas, is the cross-sectional area of the gap the same as that of the core?
Yeah, so there's a cheat that the engineers do here, which is that let's say the first order, you say it's the same. But then they have a table that they look at, depending upon the ratio of the gap width to the diameter. It's a table of corrections to the area that they're going to use. Because you do know that it bulges out. And so what they do, you go to an electrical engineering textbook, actually a magnetics engineering textbook, and it will just have a table of gap versus diameter and what corrections you make to the area. So I'm explicitly putting the gap area. Actually what you have is a ratio of gap to core, right? Which depends upon how long the gap is and the radius, the area, cross-sectional area of the gap, or of the core, right? So there's a correction that can be made. It's computationally not easy to do it all, but if you've got a table, like steam tables, then you just look it up. So they include the correction, and that's why I've done that. Okay, but for our purposes, those two are the same, for the conceptual purposes here. So rearranging, remember this is equal to, I'll break that back out, Ni, right? So I've got a relationship here that says the magnetic field of the core is equal to Ni minus H core L core times A gap mu naught over L gap A core. Okay, that's the relationship that I'm talking about there. I've got magnetic field on one side and H on the other side. There's a minus sign in there, so it slopes down. And this forms the intercept on the 0, H axis. All right? Then to find out what the actual magnetization of the material is, we'll look on this curve here. So that is that relationship. This is the property of the material. And then based upon the property of the material, you see where those two cross one another. And that tells you what the magnetic field in the core is. Right? And I have nothing more to say about that. I didn't need any numbers in there, actually. But those are reasonable examples of the kinds of numbers that would work fine here, right? If I had a structure that looked maybe more like this, got a narrow region in there, right? Then I might have to actually integrate across the region. This can get really complicated. And if I have a nonlinear relationship over there, then I've got a certain reluctance in this region where I'm going to have a certain mu, and I'm going to have a different mu over here. So it's actually simpler if the structure looks like that. And then you write your loop equation, which says that the sum of all the h's times the lengths in the regions have got to be constant. You actually, I'm not sure exactly what you do. I haven't worked this one out. I've done it for linear linear view, no problem. But if it's nonlinear, then you've got a value of mu here and a value of mu there that depends upon the ratio of the areas. But what I think you end up doing is that you make an assumption for the mu of this region and solve for the magnetization there, magnetization and B field there. Then, given that, you go back and you plug that back into your equation for the B field, solve for H. Then, given H, you go and you look up the B field again in this region and in that region, and you just continue to iterate until things stop changing. So, it should have bothered many of you, actually, that with all the calculations that we wrote up here, that you didn't actually know how to calculate the magnetic field in something as simple as a C magnet. And this begins to give you an approach to that. What I haven't done, but I can make it available, I'll put it in the notes, is how you do the calculation if you have a constant magnetization in the metal itself. Well, if you know the magnetization, then all is done, all right? But if you have a gap and now you're going to magnetize it, and mu is, you have hysteresis, then there are some corrections to this that we have to make. Okay, so that was like the practical portion of the lecture today. Let's take 5 minutes break, and then I'll go back to impractical physics.